Welcome to the Deep Dive, your shortcut to understanding the biggest breakthroughs in digital automation. We're diving deep today into something pretty exciting: computer use agents, or CUAs.
Right. These are the software agents that promise to take over those really annoying, complicated digital tasks for us.
Exactly. Like booking that multi-city flight itinerary, or maybe managing a workflow that jumps between 5 different apps on your desktop. The dream is, well, true digital autonomy, isn't it?
It is, but for a long time, getting these agents to be reliable, that's been the real challenge, like climbing Everest, digitally speaking.
So the bottleneck, as our sources really hammer home, it's this issue of unreliability, or, as they put it, extremely high variance on longer tasks.
Yeah, high variance sounds a bit academic, maybe.
It does. Let's make it real. What does that actually mean for someone trying to use one?
It means the agent is just flaky,
Yeah.
you know? It might work perfectly 7 times out of 10, but those other 3 times, it could just completely crash and burn halfway through, and you have no idea when it's going to happen.
Like a car that just won't start sometimes. So why? Why are these digital environments, our own computers basically, so tough for them?
Well, it boils down to how errors accumulate. Think about it. A complex task might need dozens, maybe hundreds of steps. Clicks, typing, dragging files. Each one of those is a tiny opportunity for something to go slightly wrong.
Like what kind of small mistakes are we talking about? A click that misses its target by a few pixels.
Exactly. Or maybe the system lags for a second, the feedback is delayed, or, a random pop-up ad appears right when the agent is trying to click something else.
Annoying environmental noise, basically.
Precisely. And the older methods, they really focused on trying to make that single agent run absolutely perfect. Flawless from step 1.
Which sounds logical, right?
It does, but that tiny error, that little deviation on step, say, 47, it can snowball. By step 90, it's caused a catastrophic failure, and the whole thing is useless.
Okay, so if trying to perfect the single run is, well, basically doomed, they had to think differently.
Right. Laterally. What if, instead of building one perfect agent, we build a system that's really good at picking the best outcome from several attempts?
And that brings us right to the breakthrough we're unpacking today: the Behavior Best of N framework, bBoN for short.
Yep, bBoN. And it introduces this idea they call a wide scaling paradigm.
Wide scaling. And the results are, well, pretty stunning, aren't they?
They really are. On Osworld, which is this really tough benchmark that tests agents on actual desktop apps, think Linux command line, web browsers, file manager.
The real world stuff.
Yeah, bBoN pushed the success rate up to 69.9%. A new state of the art.
Wow, 69.9%. That's getting seriously close to the human baseline, which is around 72%, right?
Tantalizingly close. So our mission today is to really get into how this unreasonable effectiveness, as they call it, actually works. How does this wide scaling operate, and what needed to change in the agent itself to even make it possible?
Good question. Because you can't just scale anything, right? You need a good base.
Exactly. We should probably start with the lineage, the agents that came before. It didn't just appear out of nowhere.
Right. There was Agent S.
Agent S, yeah. That one introduced what they called experience-augmented hierarchical planning. Basically, a manager agent that planned the big picture.
High-level goals.
And then a worker agent that did the actual clicking and typing, the granular stuff.
Okay, manager worker.
Yeah.
Why did they start with that hierarchy? Was it just how things were done?
Pretty much. Early large language models, they weren't great at holding onto context over really long tasks, so you sort of needed that manager to keep track of the overall strategy.
But it had downsides.
Oh yeah, it added complexity, overhead, made things a bit rigid. Then came Agent S2.
What did S2 add?
It built on S, kept the hierarchy, but added proactive hierarchical planning and something called mixture of grounding. That was about making the worker smarter, letting it delegate bits of the task to specialized modules like visual experts for spotting GUI elements or textual experts, trying to fix localization errors, basically.
So getting better at seeing the screen, but still stuck with that kind of top-down management structure.
Exactly. Which leads us to Agent S3. And this is really crucial for understanding bBoN. Agent S3 was a major simplification.
How so?
They threw out the manager-worker hierarchy altogether, just got rid of it.
Whoa, okay, but wait. If you remove the manager, doesn't the agent risk, like forgetting what it's doing halfway through a really long task, doesn't that flat structure put more pressure on the model's memory or context?
That was the gamble. And the key insight was that the newer, more powerful foundation models, They can handle it. They're good enough now to keep the short-term plan and the overall goal in their own working memory, essentially.
Interesting.
So they replace the hierarchy with a much simpler, more flexible, flat policy. The single model does both the planning and the execution. It simplifies the whole decision process, makes it faster, no need for that separate boss telling it what to do constantly.
That sounds like a pretty big architectural bet. Did it pay off?
Hugely. And there was another key innovation in S3. They built in a native coding agent.
A coding agent, meaning it could write scripts.
Yeah, right within its action space. So the agent could choose. Do I click this button in the GUI, or is it faster to just run a quick terminal command to, say, rename a bunch of files?
So it gives it more tools, more ways to solve the problem. GUI and code.
Exactly. Much more diversity in how it finds a solution.
And this Agent S3, this simplified, more flexible agent,
Yeah.
it was better even before they started doing the whole best of N thing.
Critically, yes. On its own, Agent S3 hit a 62.6% success rate on that 100-step OS World evaluation. That was already state-of-the-art. It proved that this simpler, more versatile architecture was a much better launching pad for the wide scaling they wanted to do.
Okay, so they built a better race car first, Agent S3. Now let's get into the main event, this behavior best of N. How does it fundamentally change the approach to tackling these unreliable tasks?
Right. So it starts by just accepting the fact that any single agent run is, well, a bit random, stochastic.
It might work, it might not.
Exactly. So wide scaling says, forget relying on just one run. Let's generate N runs, maybe 10, for example, all trying to do the same task in parallel.
10 attempts at once.
And then, crucially, you have a mechanism to pick the single best one out of those 10 at the very end.
That really is a different philosophy. But let's be real here. N 10 runs. That's 10 times the compute cost, isn't it?
Yeah.
Is that final, say, 7% performance boost really worth running the task 10 times? Especially if 9 attempts might fail.
That's the trade-off, absolutely. The researchers argue that the consistency you gain getting closer to human-level reliability is worth it. And the key insight is that different runs often fail for different reasons. They succeed on complementary parts of the problem space.
Meaning?
Well, one run might get tripped up by a slow website loading, but another run, maybe using slightly different timing or clicks, gets through that part fine, but maybe fails later for another reason. You only need one of those 10 attempts to actually succeed all the way through.
Okay, I see. Find the one lucky path out of 10 tries. How does this compare to older ways of trying to scale or improve agents? You mentioned stepwise scaling before.
Yeah, stepwise scaling, like in the GTA 1 work, was different. It tried to pick the best action at every single step along the way.
Optimizing moment by moment.
Right, but that's really restrictive. You might make what looks like the best click right now, but it locks you into a path that becomes way harder later on. You're optimizing locally.
Like taking a wrong turn early because it looks slightly faster for the next block.
Exactly. bBoN avoids that because it waits until the very end. It looks at the entire journey, the whole trajectory for all 10 runs, and then picks the one that actually reached the destination successfully. It allows for paths that might look a bit weird or suboptimal in the middle steps, but ultimately work out.
That makes a lot of sense conceptually, but practically. Evaluating a whole trajectory, that sounds incredibly difficult. We're talking hundreds of steps, right?
Yeah.
Screenshots, maybe code output, system responses. How do you even compare 10 of those monsters reliably without a human spending ages?
That is the core technical hurdle they had to clear. And their solution is, I think, the real secret sauce here. Something that they call behavior narratives.
Behavior narratives. Okay. Are these just like better captions for the screenshots, or is it more involved?
Much more involved. They're concise, structured summaries that are automatically generated from those messy, raw trajectories.
Structured how?
Think of it less like a video recording and more like a really detailed log file or maybe an after-action report. It specifically captures the important stuff, the action the agent took, and the direct effect that action had on the environment state relevant to the task.
Action effect summaries.
Okay.
So it notes agent click save file button and file document.txt appeared on desktop.
Precisely. And just as importantly, it filters out the noise, like the system clock updating in the corner of the screen, or maybe a window changing color slightly, stuff that happened but doesn't actually affect whether the task succeeded or failed.
Gotcha. So it cleans up the data, makes it manageable.
Exactly. And this structured format is key. They actually ran tests, ablation studies, showing that using these narratives gave a measurable boost, about 3.4% improvement compared to just feeding the judge model raw screenshots or simple, naive captions. It makes comparing these long runs feasible and, crucially, interpretable for the AI judge.
Okay, so we have these neat, clean summaries, the behavior narratives for all 10 runs. Now, how does the judge, the behavior best of N judge, actually pick the winner? You mentioned it's a vision language model.
Yes, a VLM. And the clever part is how it selects. It doesn't score each narrative one by one, like giving them a grade independently.
No. How then?
It performs a comparative evaluation. It looks at all the candidate narratives, all 10 summaries simultaneously.
All at once. How does that work?
They found the best way was to frame it as a multiple choice question, essentially. The judge model gets all 10 narratives presented together and has to choose which one represents the most successful completion of the task. It's a single round comparison.
Why is comparing them side by side so much better than just rating each one individually?
Because independent rating, which they tested using an adapted approach similar to WebJudge, just didn't work very well. The scores ended up being not much better than the average performance across all the runs. But when you force the VLM to compare them directly, side by side in that MCQ format, it can really contrast the specific action effect pairs in the narratives. It can reason about which run was more efficient, which one encountered fewer errors, and ultimately which one actually achieved the goal.
And this judge, this VLM selector, it's pretty good at picking what a human would consider a success. Because sometimes automated evaluation scripts can be a bit rigid, right? They might miss a run that basically worked, but maybe did something slightly unexpected.
That's a really important point. And yes, the judge showed strong human alignment. In situations where the standard fixed evaluation script was maybe unclear or imperfect, but a human could look at a run and say, yeah, that definitely counts as success, the bBoN judge agreed with the human evaluator about 92.8% of the time.
Wow, 92.8% alignment. That's high.
It is. It suggests the system isn't just gaming the automated script. It's genuinely identifying solutions that humans would recognize as effective and preferable. It adds a layer of robustness.
Okay, let's circle back to the headline numbers then. That jumped to 69.9% on Oswald. You said the Agent S3 baseline was 62.6%. So bBoN itself, the wide scaling and selection part, added about 7.3% absolute improvement.
That's right, a very significant 7.3% lift just from running N10 rollouts with Agent S3 and using the bBoN selection mechanism powered by GPT-4 Omni as the judge in their best configuration. And yeah, compared to the state-of-the-art before Agent S3 came along, the total jump is over 10 absolute percentage points. It's a huge leap.
And does it scale nicely? Like, does N5 give less improvement than N10?
Generally, yes. The results show performance tends to increase incrementally as you increase N, the number of rollouts. It validates that core idea. More diverse attempts plus smart selection equals better results.
And crucially, this isn't just some quirk of the OS world benchmark, right? Does this wide scaling idea work elsewhere?
It seems to. They tested bBoN on other challenging environments, too. On Windows Agent Arena, performance jumped up to 56.6%.
Oh, okay.
And on Android World, operating a mobile environment, it reached an impressive 71.6%.
So Windows, Android, it seems pretty generalizable.
Yeah.
The underlying philosophy holds up.
Exactly. It suggests that this approach, embracing the randomness, generating multiple attempts, understanding them through structured narratives, and then comparing them effectively is a powerful, generally applicable strategy for making these computer use agents more reliable across different platforms.
So if we were to sort of boil down the core lesson from this deep dive, it's really that the path to reliability wasn't about building one perfect, flawless agent.
No, absolutely not. They essentially abandoned that quest for single-run perfection. The breakthrough came from embracing wide scaling.
Running multiple tries.
But, and this is the critical part they made, that brute force scaling smart. They developed principled ways to make sense of all those attempts using the behavior narratives, and a really effective way to pick the winner using that comparative judge. It's less about optimizing one run and more about robust selection across many. An engineering philosophy shift, really.
From optimization to selection.
Okay.
And that selection process, that reliance on multiple runs, that leads us directly to a really interesting potential problem, doesn't it? A fundamental limitation for you, the listener, to think about.
Right. We've established that this whole bBoN framework, this wide scaling, it depends on being able to run multiple independent rollouts.
Independent meaning each run starts fresh, doesn't interfere with the others.
Exactly. In the lab, they can do that easily. They use virtual machines. They can take a snapshot of the starting state, run an attempt, see what happens, and then just reset back to that clean snapshot for the next attempt, 10 times if needed.
Okay, that's the controlled lab setting.
But think about deploying this in the real world. Your CUA isn't running in a clean VM sandbox anymore. It's trying to book flights on a real airline website or manage files in your actual Google Drive or maybe adding items to your live Amazon shopping cart.
Those are shared live resources, not isolated snapshots.
Precisely. So what happens when you have, say, 10 parallel bBoN rollouts, all trying to interact with your one email account or your one bank account or that one shopping cart simultaneously? That critical assumption of independence completely breaks down.
You can't have 9 agents trying to log into your email while another one is already logged in and changing things. They'd interfere with each other catastrophically.
Total chaos. That cross-run interference becomes a massive fundamental challenge. So the question we want to leave you with is this. How will future agents manage this? How can they maintain the reliability gains promised by wide scaling when operating in the real, messy, shared world where you can't just hit reset and guarantee independence between attempts?
How do you coordinate or deconflict those parallel runs when they touch shared reality?
Exactly. That's the next frontier. Solving that interference problem is going to be critical for these agents to truly make the leap from the lab to our everyday lives.
A really fascinating challenge ahead, and a perfect spot to wrap up this deep dive into the behavior best of N framework and its unreasonable effectiveness. Thanks so much for walking us through it.
My pleasure. It's exciting stuff.
We'll see you next time on The Deep Dive.